Okay, good. So the lecture is now recorded. I can see that there are more people coming, so hopefully we'll have even more participants. All right, but let's start. So now we'll have a talk given by Piotr Biskupski, who is IBM's Quantum Ambassador, and he will tell about some quantum games with IBM's technology using Qiskit and Minecraft, as far as I remember. So, Piotr, if you are ready, the Zoom is yours and we can start.
Yeah, okay, thank you very much. I was thinking that maybe I can give you also some kind of update of the technology which we have in IBM around the quantum computing, and also we can go with the fun which we can have with the qubits around the IBM Quantum. So I will show you some of the projects. I will show you some of the projects which we created, and also some projects which are externally delivered by our friends. So going back to the slide deck, first of all, our goal as an IBM is to build the quantum systems. Maybe some cases for fun, some cases for real projects. But as you can see here, what we are delivering, what we are trying to achieve is, first of all, giving the open access to IBM newest quantum computers in the public and premium access. So basically, for free, you can access the biggest computers which are available in the open space. And also through our premium partners, like Quantum Innovation Centers, IBM Quantum Hubs, you can have an access for a bigger machines, for the biggest machines which we already created. Another point, probably actually, I'm pretty sure that that we as an IBM participating very strongly with the Qiskit and on the GitHub. So basically, all the things which we are delivering, which we are creating, you can have you will have an access as a Qiskit site. I'm talking not only about uh, software, hardware, but also about the algorithm and also the additional ideas which we created together with IBM Research. Today, I will show you a little bit about that, because maybe you will be interested in what kind of systems we delivered and what kind of tooling we are proposing to the open community. The important part is that our goal is to bring to the world actually the fully operational quantum systems which you can use as an open community. I will go back to this blue slide, and you can see here right now we created more than 500 tools and resources which you can use. We are delivering the campuses and quantum event worldwide. So you can see here 21,000 plus people participated in that. And also the important part, our platform is right now delivering also the tools to create curriculums for the students, and the tools which you can use for education purposes. And basically, for last 5 years, we are investing a lot of money to create an open quantum community and to support an education systems and support education universities for the students. So today, like I told you, we will just be able to show you what we have in IBM, what we created recently, what is our roadmap, and also a little bit about the new primitives which we created in IBM Cloud. I will also tell you a little bit about the changes with the open access, because there will be something coming. So it will be good if you will know what we are showing, what we want to change. But at the end, we will have some fun also with the systems. And I want to show you also how maybe you can use those systems to create your own games or to create your own let's say so. So as you can see here, we want to create a useful quantum computing to the world. So basically, just using the NISQ machines, we want to support the system to remove all the errors which we can remove from the hardware point of view, software point of view, and primitives point of view. I will show you a little bit later what kind of ideas and what kind of systems we created recently to create something like a quantum useful quantum computers. And also, I can see the grayish part of the slide. Our idea is also to make the word quantum safe. So basically, also we are focusing on the systems which can change the potential encryption systems, encryption algorithms, which are used for the real world encryption. But I will not focus today on this. So first of all, what we changed, what we delivered recently. So as you can see here, we created something which is called IBM System 2. This system is a little bit different than the IBM Quantum System 1, which you probably know on the slides. First of all, we change a lot of on the electronics. We change a lot of on the wiring. Why? Because as you can probably notice, we are adding a lot of the new new qubits into the system. So basically, every single qubit requires some wiring. So that's why it brings a lot of it brings some challenges for us to change the approach from 27 qubit devices up to the 127 qubits and more. So that's why we change the electronics, we change the wiring. Also, we are using the new cryogenic platforms. First of all, to simplify the system. Second of all, to make the system available for not only in IBM data centers, but also in the data centers across the world. So the system, the IBM Quantum System 2 will look like this. You can see in the middle of the picture, you can see the quantum device, and then you can see the additional components of the system, which can be potentially the high performance computing servers, high performance computing platform, which is connected to our IBM Quantum System 2. The idea of the quantum system, the system 2, is to create something like a platform for high performance computing, which will use the classical approach and the classical systems connected to the quantum devices. So the hexagon inside this in the middle of the picture, you can see this is the quantum system 2 connected to multiply classical systems. But also what we are trying to achieve is to create a system which can handle, as you can see here, up to 8,000 qubits, and you can use the connections between those two systems. This is quite something, some of the uniqueness of this system. So basically, you were able to communicate between the QPUs, so quantum processor units, and then the problem which you are creating can be divided into the two systems, and then runtime you will be able to gather the information, and then you can, let's say, have the better results from your computation. If you're going to the higher number of qubits and bigger number of systems, so as you can see here, this got 3 systems connected up to 16,000 qubits, and you can see this is the multiply classical computers connected to the system. Basically, as you can see here, though, that kind of system is already created. Let's say we have those systems up and running in our data centers. And the idea will be to be able to share those systems into the other customer data centers to deliver those systems. So right now, we have multiple data centers across the world, in Japan, in Korea, in Germany, in US, and Australia, and Canada, where we are delivering our systems to our customers. So not only the IBM data centers are equipped with those machines. Okay, so if you want to go a little bit more about if you want to learn a little bit more about the system, I will suggest to watch this YouTube video, so 7AA IKUYTW, where you can see how the system is designed, how the system is working, and how we are planning to implement the multi-system connections between those systems to create something which is called 100,000 plus qubit quantum-centric supercomputer in 2033. So this idea. Okay, so this idea is first of all to use to expand the roadmap which we are showing you here, to also to build the system and scale the system up beyond 2026 to 100 plus qubits. I will show you how the system will look like a little bit later, but let's focus on the roadmap which we are showing usually our progress and what we are planning to do. So basically we are in 2023, and as you can see here, in this year we want to introduce our new chip, which is called Condor 1100 qubits. This is like a flat chip, as you can see here, and so basically it will be like a single QPU system. But in parallel, we want to create something which will use 133 qubit devices, which can be stacked together. So basically in the same machine, you will have the 3 or more processing units, and then you will be able to, let's say, divide your problem to the smaller problems, and then you can use all of those chips in parallel. So that this is the way how we are going to present a new or build a new system in 2024. And it will be like a Flamingo system. So as you can see here, it will use the systems from Condor and from Heron, and basically you will have interconnection between the chips and also interconnection between the quantum systems. So this is the idea. This is the way how we want to progress. And up to 2025, we want to introduce the system which will handle 41,000 qubit plus. And basically, every single year, as you can see here on this roadmap, you can see the green ticks. Every year we are delivering our promises to the open world. So this is the first layer. This is the layer of the hardware. But you got to remember that we are not only focusing on this layer, we also are responsible for the platform for which you as a developer can use to create your own algorithms or to create your own kernels. So starting from the circuit 2020, we created 2021 Qiskit runtime. Probably you heard about that, but I hope you will be able to use it. Today I will show you that you can use the free of charge system in IBM Cloud, but also we can give you some kind of promo code where you can use up to $500 per your calculations. Okay, another one is the dynamic circuits. This is very important stuff because finally we can create like a more advanced circuits, and we can shrink the number of steps inside the circuit. So that's why we can zero in between, we can zero the qubits, and we can easily shorten the circuit, which help you to fit into the correlation time inside the system. Another one are the primitives, but as you can see here, we are working on that, and those primitives are already announced and already available, so you can test them. They are not yet 100% working, but the error suppression and error mitigation plus error correction, this is our goal, which we can achieve. And those error suppression and error mitigation, those two ideas are already also introduced into the Qiskit runtime. I will tell you a little bit more about that. If you want to learn more, I will also give you the best course created by our friend James Weaver, who is extremely active around the circuit runtime, and he can give you his course will give you the idea how you can use those ideas. Okay, going to the top. Another point is the algorithm developments. So basically, as you can see here, we are introducing the quantum serverless, where you can have like a orchestration, you will have the circuit nighting and the circuit library. So this is like an important part, because basically those will be the tools which without any problems can help you to cut the more complicated circuits into the smaller problems, and then deliver and then send them to the processors like Heron, for example, or Flamingo in the 2024. And on top of that, you can see here, those are the model developers, and you can see that we are also trying to introduce the something which is called quantum software applications prototypes. And for machine learning, natural science, and optimization, we want to deliver the software which actually will do the main job for automatically. So the system will decide this if the problem is more quantum or is the problem more classical, classicalish, let's say like this, and it will deliver the problem to QPU, GPU, or CPU. So basically, the system will work for you. Just you will deliver the data there, and the system will decide which is the best to achieve the quantum advantage. So as you can see here, we are still working to achieve something which is called quantum advantage. So we are not looking for removing the classical calculations from the from machine learning or from AI, but we want to add additional component which will solve the problems which are unsolvable by the classical approaches. So this is, as you can see here, the IBM point of view is to achieve the quantum advantage in the near future. Okay, how we can help you? How we are working to give you the 3 different capabilities which will give you the value of the quantum computations. First one is the performance, second one is the frictionless, and the capabilities. Let's go for the performance. There are 3 main aspects. So the scale, quality, and speed. Let's go for the scale, number of qubits. So as you can see here, we already switch to the CPU-like ideas, and you have like a regular chip where you have the wiring, you have the readout platform, and then you have a qubit platform, and everything is closed as a almost regular processing unit, which is of course put inside the cryogenic system, and inside the IBM quantum system too, for example. And basically, this is the change from 2020, let's say 2019, when we started this, the quantum journey, 2016, something around that, when we put the quantum systems into cloud, where the qubits are wired kind of manually. But in this case, we are producing with the nanolithography that kind of processors. Okay, so going back to the connectivity map, this is kind of important. As you can see here, we are still working in the heavy hexagon lattice. Why? First of all, because of the errors. Second of all, because we learn from our experience that this is the design, the architecture, which will give you the best results without increasing the number of errors with the interconnection between the qubits. Okay, quality. Every single year, we are trying to achieve something which is called quantum volume. I will not describe it, but this is like a number of qubits, errors, and how many circuits you can run through the on the quantum device. So basically, you can see here we are trying to, let's say, keep the line of achieving the same, let's say, linear progress in this quantum volume. So basically, right now we are in 2020, in the middle of 2022, we have the same quantum volume of 512, but the number for this year, it will be probably around here. Okay, the speed. This is very important part, because probably you know that if you are building quite long circuits, usually it takes a lot of time for the computation. So that's why we have something which is called circuit layer operations per second. So it's called CLOPS. And this is the measuring how many parallel operations the QPU can achieve. And as you can see here on this, we are achieving let's say in the 1 month, we just switched from 300, let's say 300 in 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 uh, in 1 month we achieve up to the 15,000 of the operations per second. So as you can see here, we are changing this. Those numbers are kind of dramatic. Okay, capabilities. This is what I said about the reducing of the circuit depth. So basically, when we started our computation, we have that kind of circuits where we need to use a lot of swap gates to work with this one. But in this case, as you can see here, we can cut those circuits into the much shorter numbers. So this is one of the algorithms which is using the reducing circuit depth, and you can see that the change is quite huge. So that's why we can fit into the correlation. Okay. And the important part, it's not only that we are introducing those ideas into the theory, but also in this case, you can see here we have 18 systems which are already have those dynamic circuits, and you can use them for your computation. Okay, frictionless. This is, for me, it's also quite important because sometimes it's quite hard to describe how you can build a quantum circuit using a Python. So that's why we just switched to the idea. We work with this idea that the quantum developer will use the same tools, the same language, and the same code as a classical developer. So that's why we are focusing still on the Python, on the Qiskit, to give you, let's say, easiness of creation of the code and give you the possibility to run the code with the Qiskit open source. Okay, let's go for the Qiskit runtime. In the Qiskit runtimes, we have two different primitives. First one is sampler, which will create the quasi-probability distribution. So basically, you can see here. And we have the estimator, which will do some kind of estimation of the value of the observable value. Those two systems are available in IBM Cloud. I will just maybe switch for a second. Okay, let's go here. Oh, sorry. Forgot the password. No, it's not the one. Okay, so we are on the quantum platform. I want to go for IBM Cloud. And I will also encourage you to create an account in IBM Cloud because you can use the primitives which I'm showing for free, and you can test them inside your code. So if you go here, you will go to the IBM Quantum. You can see the overview. Okay, and now you can see the information about the Qiskit runtimes, how you can access to the Qiskit runtimes, what you can achieve with those primitives. And also what I will just encourage you to do is to find this guy, James Weaver. So on GitHub, it's Java FXpert. And in his repositories, there is a Qiskit runtime lab where you can, I think there's, yeah, Qiskit runtime lab. Yeah, where you can have, let's say, more information about the Qiskit runtime, how to implement it, and also how to add those two primitives which I showed you into your code. Let's go for the code. I did not show you the. I did. Oh, okay. I was thinking that I have a code somewhere, but it looks like I just hide the slide. Okay. But basically, if you follow the James Weaver Qiskit runtime lab, you can find those primitives. You can see how it is working and how you can use those two primitives. Okay. Why we are just introduced the runtime? First of all, because we want to let's say shrink the time of the latencies inside the computation. So basically, you have that say near time classical, real time classical, and the quantum. As you can see here, using the quantum assembler, we are in some of areas of the milliseconds. But basically, if you'll use a runtime, you can make your computation much faster. You can be closer to the near real time computation. How it works? So basically, your Qiskit program go to the queue, then you have the Qiskit runtime quantum code, and it will just switch to quantum assembler circuit, and that will send you the quantum hardware. So basically, as you can see here, it's this low latency interaction, and you can use them directly from your code. Probably I have the code somewhere. If you give me couple of seconds, I will show you those how it works. Okay, let's go for the middle of quantum. This is the idea of the 100+ qubit quantum-centric supercomputer, which we are working together with the 3 universities. And as you can see here, we will create the, let's say, clustered systems, and we will interconnect them with the quantum connections. Those will be the quantum transducers and the optical connections between the systems. So this is like a additional network to exchange the informations in between the quantum systems. And of course, we will have those classical connections, because you can see here we have those classical computers, and over here and over here. And every single system will have 25,000 qubit clusters. So this is like a per each of the data centers, and then we have those two interconnections between those data centers. And this is our goal, which we want to achieve in 2033. This is quite something new, which we are trying to achieve. And as you can see here, we want to invest for this initiative a lot of money to make this cluster work. Okay. I mentioned about this circuit nighting toolbox, and there are 3 different components: so embedding, entanglement, forging, and circuit cutting. This is the idea which you use if creating your code. You can use them. For the sake of the time of our presentations, I will not focus on them. I just showing you what we have and what you can use during your experiments with the quantum systems, and how you can break down the, let's say, more complicated system to the smaller problems, and then you can just send them to the smaller processors to use the parallelization of the computation inside our system. Okay, I mentioned a little bit about the noise and about the estimation of observables. So let's show you the 3 different ideas. So error suppression, error mitigation. So the error suppression is reducing the errors, adding some additional components into the circuit. So basically, you can see here we have those X gates, which are added into the circuits, which are doing nothing actually, because you can see here this is another X gate which is not doing. So basically, 2X will give you nothing, but it makes let's say it will create like inside the circuit small block, which will in our experiments, in our tests, it shows that it is suppressing some errors which can appear on this part of the circuit. So basically, during the measurements, we found that when we add those two different X's, those two the X gates, the system is reducing number of errors. Another one is error mitigation. And you can see here uses outputs of ensemblements of the circuits increase accuracy of expectations values. So basically, you can see that we are modifying a little bit the circuit, and then we can mitigate those errors into the in our circuits. And as you can see here on the post processing, using the mitigation and suppression, adding some kind of post processing component, then we are achieving the estimated values of the system. Okay, so how you can use it into the code? As you can see here, we can just use the estimator session options, job estimator, and then you can add those informations into your code and easily use those ideas. The same, actually, I will go back. Actually, using the Qiskit runtimes, you can use them directly. So that's why I mentioned that it will be kind of useful for you to open the platform and use the Qiskit runtimes. Okay, this is what I want to show you about the roadmap, about how we are developing our systems from hardware point of view and the software point of view. But okay, let's have some fun. Let's see what we did recently, what kind of ideas came to our heads using this the work. But this is the moment where I want to show you something. So first of all, you can see here we have this Qiskit runtime in IBM Cloud, and as you can see here, the quantum system and simulator access is the $1.6 per second. So it's kind of expensive. So that's why please just use the voucher. And the voucher is, first of all, you can use 127 qubit devices in IBM Cloud. So those are the systems which usually you don't have an access to. With the promo code Quantum23, and you will have 500 USD for every voucher. So for your, let's say, ideas, for your code which you will create, please use this voucher. And thanks to this one, you will be able to use the quantum devices. So let's go for the systems. Which are available in the for Qiskit runtime. Important part is, I want to show you something which you probably noticed. So this, as you can see here, in the free resources, we have the Brisbane 127 qubit device, which is the processor type is Eagle R3. But if you will go for all systems, you can notice probably that there is bigger number of 127 qubit devices. So this is the biggest change for us for open systems. Basically, previously we have had a lot of the systems where we have the 5 qubits, 7 qubits, and something like this. But as you can see here, the number is kind of changing. So what we want to introduce, first of all, we want to exchange all of the smaller systems, as you can see here, to the 127 qubit systems. Basically, we know that they are performing the best. The Eagle R3 is the best performing quantum processing unit. So that's why we are changing the open access to 127 qubit devices. Of course, there will be some kind of limitations. Those limits will be related with the number of minutes where every open user can consume per month, but those informations will be soon available, and we will just give you we will give you the informations when this open access will change for in this year. Of course, we still have some of the systems available for the computation for some scientific projects. So basically what you can do, you can just give us a call and we will give you the access for 127 qubit devices or plus for your scientific projects. Another point is, of course, always you can you can ask to open a project inside the IBM Quantum Innovation Centers, where you can have an access to 433 qubit devices and the higher, with the, of course, with the longer time, with longer computation time. So again, just write down the promo code is available now. So $500 for 127 qubit devices, which I think will be very useful for our hackathon. Okay, so I remember that when we had the first hackathon, game hackathon, I showed you the Entanglion, which is the board game created by IBM Research. This is like a cooperation game, which you can play on the board during the hackathons. Actually, we played the game on one of the hackathons together with our students, and they enjoyed the game. Like I said, it's a board game, it's a dice game, so it's a big fun. And actually, what I like, you are learning what exactly, how exactly you can use the gates. You have different event cards, and you have, let's say, components which you need to gather. Let's say the team need to gather all of those components over here. Like I said, fun game. I will encourage you to check the GitHub Entanglion, where you can download and print the board and print the dices and use them. But also you can buy in Amazon. You can buy the game in the cardboard. Okay. We also, I know it's not a game, but I want to show you how differently you can use the systems, how differently you can work with the qubits. And this is something which we called Quantum Coffee Maker. So this is Coffee Maker. And the system was created like this. We have the Coffee Maker, which have their own API. This is the guy. It's connected via Wi-Fi to Raspberry Pi, which is hidden over here into this box, which looks like IBM Quantum System 1, where the Python and the Qiskit is running. Then you have and of course, the system is connected to IBM hardware, IBM quantum computers in IBM Cloud. And what user can do, yeah, let me just try to find yeah, this is the one. Okay, let's go this. Okay, what users can do. As you can see here, we have this this is the Qiskit composer, where we have the gates and we have, let's say, 3 qubits, and you can place your gates on the quantum register, and on the classical register, you will have the information taken out from the circuit. And thanks to this one, you can determine which beverage you can get from this coffee maker. So basically, if you will have, say, 000, you will have a tea, and so on, so on. Why I'm showing you? First of all, because it's kind of educational game. It's an educational system where we can show to the broader audience how the computation works, how the gates are working. And also, at the end of the day, you can have a nice coffee. Coffee is very tasty. And also, what we found here, we can somehow challenge people who are more advanced with the quantum computing to create a code, create a circuit, for example, which will create only the coffees with the milk. So basically, in this case, you need to have like a 1 on the last bit and 00110101, for example. And you can challenge people to create that kind of circuit. And I want to tell you one fun fact that even people who does not have any experience with the quantum computation, they were able to make a nice to solve the puzzle with the coffee milks, which is kind of cool. So you can download the code of the coffee maker. You can build your own system. Everything is described on the GitHub, and there is only one problem. You need to buy a coffee maker with an API and with internet connection. But I think in those days, it is kind of possible. Okay, going back to the my favorite guy to follow on the GitHub, which is who is James Weaver, is a developer, and he is extremely passionate about the quantum computing and the music. I encourage you to check his GitHub. He had a lot of ideas how you can create games, how you can create solutions which will consume quantum computers as an input source. So for example, in this here, you have the Qiskit block. This is like a game where you can just create your own, which is creating the quantum world where you can solve the puzzles and use, I think right now it's around 13 escape rooms where you need to solve the puzzle and get out from to the next room. And also what I like, he created maybe I will show you his. I will go back to James. Yeah, this is the guy. And right now there is it's a Qiskit block mine test release. It's a this is brand new, but I like also this quantum music playground where you can see how he was able to change the quantum circuit into the music. You can create you can use the quantum gates to put them on the different instruments like here, and it will just create you a very nice music. And you can see this is how the circuit looks like. And here is I need to let's wait a little bit for the graphic in here. You can see how it is adding the gates, adding the music into the system. Yeah, this is the one. So you can even find the real music created by the, so you can see here. We have the basic states, we have the stations, and you can see how we are adding additional notes into the instruments, and then you can just play the music as it is. So kind of cool project. So I like the project, so that's why I'm sharing this one with you. Qiskit blocks is very useful. Usually when I'm just having a conversation with the kids from the ground school, we are playing with the Qiskit blocks. We are trying to solve the puzzle. It works quite well. So you can see here we have those escape rooms where you need to solve the riddles and the puzzles inside every of the rooms. Okay, this is like a playground, which I mentioned before. So basically you can see here, you have the pitch, you have the phase, you are adding you're creating your circuits, and the circuits will be then switched to the nodes and send it to the instruments. I like this idea. It works quite well. And also what you can do here, you can add this the music, let's say your circuit into the real music composed system, and you can create your own music. I will not play this one for you, but you can go to the GitHub and you can find it. Okay, and the last idea from James was the project which was implemented under one of the mentoring Qiskit Advocates mentorship program last fall. And project description you can find, of course, on his GitHub. This is, let's say, a classical NIM game, which was changed into the quantum-ish like. So basically, you are playing with the human classical computer, or you are playing against the quantum computer. So you can see here, you can find this application on his GitHub. Like I said, I will encourage you to find it because there is a lot of nice information, and also it shows you how you can build your own game. Okay, every single year in Finland, there is a quantum wheel game. And recently, I was checking what kind of games on the last quantum game jam was created. And I was surprised because in 2021, there was around nine of the submissions. But this year, there's much more. And you can see here, they are much more advanced and looks like that they have a lot of fun. So you can go and find those games. Maybe you can find something useful for this. Okay. There is another person on the GitHub. I will not try even to pronounce his name, but you can see the link to in here. And first of all, why I'm showing you that? Because he has his own repository of the quantum games, which you can use as a kind of example. But the important part, he also is showing you the engines which can be used on with the Qiskit to create the game. So Pygame, Unity, Mindtest, and Jupyter widgets. And basically you can use all of those ideas. I will encourage you to go there and check this link. Okay, guys, we are almost at the end of my talk. And first of all, I want to tell you one thing, that stop thinking classically, go quantum, try to go above the classical approach and above the classical thinking. That's why this is only one way how you can create something new, that you will be able to create something which will give you the prize, the first 3 places on this hackathon. And I want to also just give you one other announcement, that the winning team will also receive from IBM Cloud the voucher for $5,000. So this is our addition, Pavel, to the prices which you already announced on the web page of the hackathon. Okay, guys, thank you very much for your for this meeting. Thank you very much for that you give me the possibility to share my thoughts and share the roadmap with you guys. Thank you very much again.
Great. Thank you, Piotr. Thanks for this great presentation. Very informative. Great hints. So just information to the participants. I think I didn't tell it at the beginning, but Piotr is also, so you probably have seen it on the website. Piotr is also a member of our jury committee, so he'll be one of the jury members evaluating the submissions. So you can take his hints at the end seriously. And from my perspective, I can also tell that this creativity and thinking out of the box is very important to create something new. And yeah, that's a very good news, the announcement of the special award for the best team. So that sounds really great. So thank you, Piotr, for that, and yeah, thanks to IBM as well. Do we have some questions maybe to Piotr? We still have a few minutes. I'm not sure if Piotr has more time, but maybe there are some important questions now.
If not now, you can just send me the message. You can share the message on the chat on the Discord. I will follow the Discord information. So Pavel, just for all of you. I don't know if you maybe I will just, if you have still a couple of seconds, I will maybe just give you those. I will share the links to the James and to the GitHubs, which I mentioned, because maybe it will be useful, guys, for to use it. So
Okay.
this is the first link, and the second link will be the James's
All right.
GitHub.
Uh, So there is a question about accessing the voucher. So I believe that
Yeah.
this, yeah.
How do so the voucher, you need to just, when you will create the resource of the Qiskit runtime in IBM Cloud, you are just there is a place to put the name of the, let's say, the code of the voucher, and they are putting
Mhm.
the code, and you can use the
Mhm.
code for it. So basically,
Okay.
it doesn't matter if it's this old account, it's this new account. You're adding the voucher when you are creating the Qiskit runtime. That's it.
Hmm. Okay. And this voucher, I mean, this $500 is for everyone, right? So it's not only for the
Yeah,
participants.
everyone who is creating who will have an account can use this one. So basically,
Great.
if the team consists 5 people, you have $2,500 for to use it during the Qiskit for the on the Qiskit runtime, which is kind of cool, I would say.
Yes, yes, indeed. That's very good. Um, all right. Do we have more questions to Piotr? Piotr, can we also sh maybe share your email address, or do you prefer
Yeah,
to?
yeah. No, no,
Okay,
no, no. It's no problem. I just typing my. Okay, here is my address. So you can just type, you can write the message to me. One disclaimer, I'm just heading for a vacation, so I will be not very responsive, but I will try to answer at the evening.
hmm.
My
That's
wife is
that's
sitting
good.
my wife is sitting next to me and saying no, 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 but guys.
Okay, standard. All right, so we'll also add it to the spreadsheet with the list of mentors, let's say. And yeah, that's good. Do we
Okay.
have more questions to Piotr? Maybe last chance, last opportunity to ask a question now on Zoom. So
Yeah,
later you can contact
yeah.
Piotr
I
by
had one
email.
question.
Yes, yes, go on.
Yeah, I just wanted to know, like, what are you looking for the special category, like, in case of, like, like when you are evaluating. So, just wanted to know, like, what things you are looking in for.
It was question to Pavel or to me?
You.
To me. I'm looking the creativity, because as you can see, I'm checking almost all of the repositories with the quantum games, and I want to find something new, something creative, something like as I just wrote to you guys, that stop, do not think classically, do not think the classical games, do not try to exchange the classical games to the quantum games, like, because everything like that work, it was already invented. So the quantum pong, this is the game where actually was the first game even created. Quantum chess, yeah, okay, cool, but where is the creativity, where is the novelty of this one? So
Yes.
basically, try somehow to surprise us with the new ideas, new approaches.
Hmm.
Yeah, I think you will be surprised. Yeah.
Thank you.
Good.
I'm waiting. This is I'm waiting for. Okay,
Yeah,
guys.
I can tell that there's one team that selected the name Quantum Chess, but I'm not sure if they are also going to develop Quantum Chess game or something else. But anyway,
Okay, guys, I need
maybe
to
good. Yeah,
disconnect
good.
because I need to
Thank
go
you, Piotr. Thanks once again. I will now stop
for work.
recording as well.
Okay, doke. Thank you very much, guys, and
Thanks.